This is the hydrolysis of water. We know that water is H2O, 2 hydrogens to each oxygen, and we're just going to provide some electricity to split the water into oxygen and hydrogen. This is actually going to be a really important energy technology, because you can use an energy cell. You don't have to do it this way, but you can use electricity using a fuel cell to divide water into hydrogen and oxygen. What we usually do is vent the oxygen to the atmosphere, because there's always more there that we can grab back from the atmosphere, and store the hydrogen as a fuel. So one of the important fuel technologies for Australia is going to be hydrogen capture, storage, electrolysis. So it allows you essentially to do what every other battery does: get electricity from where it is to where you want it. So you can, the advantage of hydrogen as a fuel is that you can very quickly fill up the tank. It's like filling up a tank with petrol effectively, or with LPG, rather than having to charge like a Tesla or other current battery car has to charge. So what we're going to do is work out the molar volume of a gas, in fact 2 gases, because both oxygen and hydrogen will be produced. So let me explain the setup here a little bit to you. We have a tub of water. We've added to it some sodium hydrogen carbonate, otherwise known as sodium bicarbonate or bicarb soda. It's the same thing that you buy at the supermarket to use in your cooking, but this is analytical reagent grade. It's very expensive and accurate, but for our purposes it doesn't actually matter that much. We threw some in there because we want our water to conduct electricity, and pure water doesn't. Pure deionized water doesn't conduct electricity much at all, because it's not dissociated much at all. It's mostly H2O molecules, very little H plus and OH minus. But by adding some other kind of ions, in this case sodium and hydrogen, because it's sodium hydrogen carbonate and carbonate ions, we get that conductive behavior in the water. We have 2 very precise measuring cylinders to measure the gas produced. They have carbon electrodes inside them, and we are driving that with our power pack. We're measuring the current travelling through the system, and we're measuring the time for which the current flows. So by measuring those 2 things, we can work out how many moles of electrons have travelled through the system, and therefore how many moles of the gas have been produced. And we can assume that the pressure inside these guys is very similar to atmospheric pressure, and our atmospheric pressure and temperature today in this lab in the Gold Coast is very similar to standard temperature and pressure. So the volume of gas we produce should give us a sense of the molar volume of hydrogen and the molar volume of oxygen, because we'll know how many moles of electrons we've actually used in the system. So I'm just going to turn on the system and the stopwatch at the same time. I've got to wake up my stopwatch first. No, please go away, Siri. Right, we will start that and start that. So you can see that we're running for a certain amount of time. We're on a milliamp range of DC current, and we've got 0.02 milliamp flowing. So that's not a lot of current. That's a relatively small current, but that should be sufficient to get us some bubbles on our electrodes, and it should be sufficient to separate the water into oxygen and hydrogen. I can already see some bubbles forming, actually not on the carbon electrodes, but on the tips of the alligator clips that are grabbing the carbon electrodes. But we definitely are getting gas produced inside the cell, and now we're starting to get some bubbles on the surface of the electrodes. We were moderately sure about which gas would evolve at which electrode, but it's actually really easy to tell given a couple of minutes, because twice as much hydrogen will evolve as oxygen. So we will actually then be able to say, all right, that one's definitely the hydrogen one, that one's the oxygen one, and write down those measurements in terms of distances. So that's at 20 seconds. That's going to take a little while. You can see it bubbling up there. You can see a bubble starting to form at the top actually of each of the 2 cylinders. We will leave that going for a few moments, and then we'll take some measurements. So we're at just a fraction under 20 minutes. This is a feasible experiment to do in one 40 or 50 minute period. You'd probably want to get started on it at the beginning and take your measurements close to the end. If we had the rest of the afternoon, we could wait a bit longer for more gases to evolve, because it's just going to continue at the same rate and in the same way. But what we'll do at this point is stop the timer, which keeps going to sleep, and stop the power. So maybe we'll give it a minute. We'll wait till 20 minutes. Again, we need to measure it about 20 minutes precisely. So we'll have it to 100th of a second, which is probably a little bit more precision than we really need, given that we only have one significant digit on this one. And we'll stop both things at the same time. So 20 minutes and 7/10 of a second. You can see that fairly easily there is more gas in this one than this one. So this is going to be the hydrogen. This is the one that's coming from the positive electrode, and the oxygen is coming from the negative electrode. Let's test the gases just to be sure. We're fairly confident because of the different volumes, but now that we've turned it off, we will put the other issue that we've got is that I've got to be very careful not to let any air in, because that would mess up our measurement. So I'll get the electrode out and put a bung in so that we keep our sample. Now there are also some bubbles on the side. I don't know if you can see that on the side there are some extra bubbles of hydrogen that haven't made it to the top. So I'm just going to flick that a little bit and get as many as we can into the top of the syringe so that we can take a measurement. We'll do the same to the oxygen in a moment. And if we read that scale we've got at eye level, about 3.2 millilitres of hydrogen gas in that one. So we would expect about half as much oxygen. I'm not super confident that we've got that much, but let's find out. Maybe we'll do a pop test on this first. You know that hydrogen gas is flammable in air, so if we ignite it, it should go pop if there's enough. I'm not super confident that there is enough, but if there is, we should get a popping sound when we ignite the hydrogen. I might just use the match directly. So no, I don't think we had enough gas there, and the air overwhelmed it. So that's the test that you would do if you had a significant volume of hydrogen gas. That pop test would demonstrate that it's hydrogen gas to your students. So let's just take our oxygen while we're at it though and check our measurement. So we said 3.2 millilitres of hydrogen. So we should have 1.6 of oxygen. So I'm going to make sure that any that's hanging on the electrode goes as well. Again, I want to get any extra oxygen that's clinging to the side of the syringe to be part of the bubble, because it's the bubble's volume that we're measuring. And if we squint real hard and hold our mouth right and imagine, it's probably 1.6. I suspect it's a bit closer to 1.2 milliliter of oxygen that we've collected. And similarly, we could do the splint test. I'll demonstrate that, but again, I don't know that we have enough gas to make it really work well. The splint test is if you have something that was a flame, barbecue skewers work really well. They work much better than matches. For whatever reason, what they're made out of will continue to glow like that for a long time. If you put the glowing thing into a bubble of oxygen, and there's enough oxygen, it will burst back into flame because oxygen drives combustion. And if there's sufficient oxygen, it will turn a glowing splint back into a flaming splint. And that's our test for oxygen. So we could use those tests if we had sufficient volume of the gases. But what we have demonstrated, is we've separated water into hydrogen and oxygen. And because we know the current that was flowing and the time that it was flowing for, we can use that to calculate the molar volume of both hydrogen and oxygen, but our oxygen number's a little shaky, so we'll just do hydrogen for our calculation. So I guess I should say it right at the start of this one, I suspect the result will be wildly inaccurate because we just didn't have time when we were shooting the video in the lab to just leave it run long enough to collect a decent volume of gas. So if we'd had the opportunity, maybe I should actually explain a little bit. We shot these videos in June 2020, towards the end of the COVID crisis. We were allowed to be on campus for a very short amount of time to conduct the videos, and then we had to leave. So time was very much a constraint on the shooting of the videos. That's also why I'm wearing the same shirt in many of the videos, because we shot 18 videos in 2 days. It was crazy go nuts. So ideally, we would conduct this experiment much more accurately and precisely across, maybe 4 or 5 hours, so that we collected a bigger volume of gas and it was more accurate. But given all that, this is what we actually got by way of results and the calculation that we can do on them. So I guess the first thing to note is that when we talk about the molar volume of a gas, it's how much does what volume does that 1 mole of that gas fill at standard temperature and pressure. Now, just a reminder, standard temperature and pressure since 1982, prior to 1982, standard of temperature and pressure was 0 degrees Celsius or 273.15 Kelvin. And one atmosphere of pressure. 1 atmosphere of pressure is 101.3 kilopascal, or 1.013 by 10 to the 5 Pascal. But it was changed in 1982 by IUPAC to exactly 100 kilopascal, 10 to the 5 Pascal. So standard pressure is now that. It's only a very slight, it's about a 1% change, but that's the correct definition of standard temperature and pressure. Now, in our lab, at the time of the experiment, it was 22 degrees C, and we will assume 1 atmosphere pressure because we didn't have a barometer handy, but there was no major impending thunderstorms or anything like that that would take us far away from basic atmospheric pressure, and the Gold Coast lab is pretty close to sea level, so that wouldn't change the pressure as well. So let's call that 1.013 by 10 to the 5 kilopascal. Oh, sorry, by 10 to the 5 Pascal, or 101.3 kilopascal. So we're going to have to adjust for that. We're going to use the gas laws to actually adjust the answer that we get from calculating the molar volume of the gas from the temperature and pressure we were working at to standard temperature and pressure. Now, this is one of those ones where we know the answer. For an ideal gas, and we talked in the lecture slides about what an ideal gas is, but for an ideal gas, at standard temperature and pressure, the volume is 22.4 litres. So we expect that for hydrogen, which is pretty close to an ideal gas, we we'll get something on the order of 22.4 litres. Now, I suspect we won't. I suspect we'll get something different because of the inaccuracies with our experiment, but let's find out. So we kind of know the ending of the story. This is actually probably a useful teaching point to talk about, which is that for students, the temptation is to treat it like a mystery novel. You don't find out who the murderer is until the end. You don't find out the answer until the end. And many times that's a good impulse because it's an inquiry approach and they're trying to find out the answer. But other times it's worth actually telling them the answer and then establishing how we get there, because that's also an important part of teaching the things that we're teaching when we teach sciences. Right, so what did we do? We passed electric current through a cell to hydrolyze water into hydrogen and oxygen gas. So the reaction effectively is H2O plus, gives 2H plus, which then go to form H2 gas and 1O2 minus. So those will also combine to form oxygen gas. But if we treat this as that it ends up as H2, let's look at the hydrogen side. We did also measure the amount of oxygen, but we pretty much just fudged that by halving the amount of hydrogen because it produces twice as much hydrogen, because if we look at the final reaction, we end up with a half O2. So that means that essentially we get half as much oxygen as hydrogen. So we'll just follow through with the hydrogen because that was the more accurate measurement. We got VH2 equals 3.2 milliliter, because we're measuring it in the thermometer cylinder, equals 3.2 by 10 to the minus 3 litre, because we're working in litres. Apologies that my threes are looking weird. I think it's the way the tablet is picking up my hand movements rather than the way I'm actually writing them. Now, the key bit for our purposes is that each of these requires 2 electrons to happen. So 2 electrons are being transferred. We also included a salt in the liquid so that we ended up having the equivalent of the salt bridge that we have in the galvanic cell that we look at much later in the course. We needed to stabilize the charge overall, but each of these transformations, each of these hydrolyzations of water into hydrogen and oxygen requires 2 electrons. So for each 2 electrons that pass, we should get 1 mole of hydrogen gas. Or sorry, for each 2 moles of electrons that pass, we should get 1 mole of hydrogen gas. Okay, so hopefully that's relatively clear. We need to find out the total current that passed, the total number of moles of electrons. So charge Q equals I, the current, in ampere, times T, the time in seconds. And in this case, we were passing a current of 0.02 ampere and we passed it for 20 minutes, which is 1200 seconds, 60 seconds in a minute. So that ends up being a total of 24 coulombs of electrons, 24 coulombs of charge, but obviously it's the electrons that are traveling, that had passed through. And to find the number of electrons, the number of moles of the number of electrons initially, we take our 24 coulomb and divide it by the charge on the electron, which is 1.6 by 10 to the minus 19 coulomb. And that gives us 1.5 by 10 to the 20 electrons. So that's a lot, because electrons are tiny and there are many of them in each coulomb. 1.5 by 10 to the 20 electrons were passed, and then we want to know how many moles of electrons were passed. So actually let me correct myself there. I'm going to make that a big N, because that's the number of electrons, like the literal number of how many there are. And then let's do a lowercase e for number of moles, because that's what we use in chemistry. So number of moles is going to be that 1.5 by 10 to the 20 divided by Avogadro's number, 6.02 by 10 to the 23. So, and that gives us a result of 2.49 by 10 to the minus 4 moles of electrons. Remember, you can have moles of anything. You can have moles of elephants if you want. A mole is just a number of something. It's Avogadro's number of anything. So 2.49 by 10 to the minus 4 mole. Now, for that many moles of electrons, it takes 2 moles for each reaction. So that many moles of electrons is going to give us half that many moles of hydrogen gas, H2. So we can do N, number of moles of H2, is just that number divided by 2, which is going to give us 1.25 by 10 to the minus 4 mole. Right, now we know how many moles of hydrogen gas we should have produced. This is the theoretical yield of this reaction based on the amount of current that we passed for the amount of time that we passed it for. So to find the molar volume, the number of moles, which is a number in moles, is equal to the volume we've got of the gas divided by the molar volume. We want to find the molar volume, so we'll make the molar volume the subject. Now the volume of gas that we got, it's written up the top there somewhere, was 3.2 by 10 to the minus 3 litres. Let's do the issues. And the number of moles we just calculated, is 1.25 by 10 to the minus 4 moles. And that's good because that means the unit that we get out of this is going to be litres per mole, which is an appropriate unit for molar volume. If my calculator is correct on that, I end up getting something actually not too bad. Let me just run the calculation. I end up getting 26.666666. Good metal number. So let's put that down, equals 26.6, and then we'll call it 7. We'll round it to the appropriate number of decimal places. In fact, that's probably one too many. I'm going to actually correct myself. We've been working to 3 significant figures, so let's work to 3 consistently. 26.7 litres per mole. Now you remember I said that the canonical number from the literature is 22.4, so we're not a million miles off. But hang on, we've skipped a step. We haven't yet calculated the transferred that to standard temperature and pressure. So at our laboratory, which is hotter than standard temperature, we get this. So the number should actually, I think, be a little smaller. So I'm just going to create an extra sheet. So we got Vm, the molar volume, equals 26.7 litres per mole. But that's at the temperature that we've got, temperature and pressure that we've got. So let's use this combined gas law, P1 V1 over T1. This is Boyle's, Charles and Gay-Lussac's law all combined into one. P2 V2 over T2. And it doesn't matter which is 1 and 2, and we want a volume as the solution. So let's leave V1 where it is and reorganize to make that the subject. So V1 equals, well, it's going to be P2 V2 multiplied by T1, because we just multiply both sides by that, and then divide both sides by P1. And we've got the overall expression, which we can sub in. So P2 is the pressure that we had in the lab. 1.013 by 10 to the 5. V2 is the volume that we found in the lab because we're trying to correct that for STP, 26.7. T1 is the standard temperature. So let's work in Kelvin, but let's work in whole degrees because we measured our temperature in whole degrees. So 273 Kelvin divided by P1 is the standard pressure, which is 1.0 by 10 to the 5. So the pressure is not going to change very much. The temperature is going to change by 22 degrees in 273. So a couple of percent. No, not even that. So what do we get for our final volume? So this in the end is the correct molar volume at STP of the substance. Again, give me a second for the calculation. Okay, I ran that calculation and discovered that I got 7,000 because I failed to put T2 on the bottom line when I corrected. You may well have been screaming at the screen. So it was there initially, and when I reorganized, I missed putting it there. So it's that kind of thing where you understand that the answer makes no sense, so you can check it. And again, this is something you will want to be teaching your students. As soon as you get an answer out, don't just write down what the calculator says. Go, does that make any sense at all? 7,000 when I'm expecting 20 something clearly doesn't. I've made a mistake. Where is it? So, and it should be 295 because it's 22 degrees C, which is 273 plus 22. So if I now divide that 7,000 by 295, I get 25.03 litres per mole. So actually, given the roughness of our apparatus and the shortness of time, that's a respectable result when what we're looking for is 22.4. To get 25, it's off by 15%, something like that, very roughly in my head, but it's not awful. So certainly in your write-up you will talk about the known canonical value, the sources of error, etc. But we basically did calculate it. The key thing with this and the trap for young players that the students often miss is they'll get out that first answer, the 26.7, and forget to change it to standard temperature and pressure, which is what we're looking for. So there's really step one, find the molar volume at laboratory temperature and pressure, and step two, convert it to standard temperature and pressure. Thanks all.